Hey AP Calc AB, just making a video here for your work you've done the last couple of days. This is problem set 6, looking at separable differential equations, initial value problems, u-sub, all that. So just going to kind of walk through the solutions. So just to start off, I wanted to remind you what we're looking at here. You know, for separable differential equations, we're looking at a differential equation which is the equation of a derivative. Oftentimes that's shown by like a dy dx equal to something, or a y prime equal to something, or something of that nature. And if it's a separable differential equation, well, that means we've got two variables that are involved that can basically be written as a product, or one variable is involved in a function times a different variable involved in a function. So like a gx times a g of x times a h of y type thing. And so then we can separate those variables using either multiplication or division. So if we start with what's written up here, we would divide by h of y to bring it down here, and we would multiply by dx to bring the dx over. Then we would integrate both sides, each side separately, with that ultimate goal of solving for y. And so that's just kind of a review of what separable differential equations are and differential equations in general. And notice down here I said remember that differential equation in the form of dy dx equals k times y is a separable differential equation, even though there's no x involved over here. 1 is basically the function that we're using, or k is the function that we're using as the function involved with x. And so then is a separate. So if we separate that out, we divide by y, multiply by dx, and we'd get this integral of 1 over y dy equals the integral of k d. That should be an x right there, k dx. So and then from there, when we integrate, we end up with that PERT form is what we used in class. In this case, we're using a instead of p, and then k instead of r. So this is just showing, you know, if we integrate 1 over y, we get the natural log absolute value of y. We integrate k, we get kt plus c. Remember that we just used the c on the right side, and then we take e to both sides to get e to the natural log of y. The e and the natural log cancel out, and then I have to take e to the whole side. Don't forget the plus c is now in the exponent here. That's a very common mistake. And then one of our properties of exponents is if we're adding in the exponent, we can separate as a product, so that e to the kt plus c over here, got a little messy, so that e to the kt plus c over here is the same as e to the c times e to the kt, and then we just replace the e to the c with another constant, generally called a. So that's just your review of solving that separable differential equation. So here on this first problem, it says find the equation for the population y. Here's our differential equation, very similar to what I just talked through. So I'm just going to go ahead and solve this. What I'm going to do is I'm just going to separate out by dividing by y and multiplying by d of t. So I have 1 over y dy equals 2.3 dt. And then from there I'm just going to integrate each side separately. And so you can see here I integrate 1 over y and get the natural log absolute value of y, integrate 2.3, and I get 2.3t plus c. Then I take e to the natural log of y and just get absolute value of y, and e to the 2.3 t plus c, and that stays the same. So e to this addition right here can be split up into a product, and then I just replace the e to the c with an a. And now at this point, we were told there are 2,000 bacteria initially. So that's the same as saying when t equals 0, y is going to equal 2,000. So I'm going to apply that to solve for a. And so there you have it. I noticed I put the a I put the A here but didn't take off that C. That C shouldn't be there. Hopefully you caught that, but otherwise I just caught it for you. And then I put the 2000 in for Y, and then the 0 in for T. E to the 0 is 1, so that just gives me A is 2000, which then tells me my answer here for A is going to be Y equals 2000 e to the 2.3 t. So that'll be my answer there. And if I want to find the bacteria at time equals 7, well then that's like saying, well, what's y of 7? And so y of 7 is going to equal that 2000 times e raised to the 2.3. What do we got here? 19 billion, 641,341,840 bacteria. That's kind of a lot. So there's that first problem, A and B. So here on this second problem, it's kind of a similar setup, right? We've got dy dt equals k times y, where k is a constant, t is measured in years. We're told the population doubles every 8 years. Which of the following could be a value for k? So at this point, it is fine to just recognize that that's a differential equation of the solution that would be in the form y equals a e to the kt. We just walked through and solved that, and so now we're saying when we know the population doubles. So whatever a is, we're saying we want the time when y is equal to 2a. Okay, and so it doesn't matter what the initial population was. After you write this, you can very quickly see, well, the a's are going to cancel out, and so then we're looking for when does 2 equal e to the kt, and then from there we're solving. And we were told doubles every 8 years, so I could plug in an 8 right away also for time. So if I plug in that 8, that becomes fairly easy here. I'm going to simply take the natural log of both sides. That's an 8k, and then that's going to give me the natural log of 2 is equal to 8k, and so the natural log of 2 divided by 8 will equal k, and that's going to be our answer. That's approximately 0.087, so that looks like A. So on number 3 here, it's a similar situation, only now we do have an x and y that shows up. And so what we can recognize is we do have an x times y, and a dy dx is what that's equal to. So that shouts to us, hey, this is a separable differential equation. And so now I'm going to separate out by dividing by y and multiplying by dx and going from there. So what I've got going on here is I'm saying what I just said. I integrated both sides separately with respect to dy on the left and dx on the right. Integral of 1 over y is natural log of absolute value of y. Integral of negative 2x is going to be negative 2 times 1/2 x squared. And then again, I'm kind of simplifying down, solving for y here, and then that e to the c is equal to the a. So now from here I'm told y of 1 equals 4, and so I'll be able to finish out this problem and solve for a. Alright, so I plugged in the initial value here and got, I plugged in a 4 for y, and I plugged in a 1 for x, and so that gave me a times e to the negative 1, which is the same as a over e. So I multiplied the e over and got a equals 4e. So then I plug that back into the general form here, plug the a equals 4e back in, and then just manipulation here. So this would be the same, looking at this line, it's the same as e to the 1 times e to the negative x squared. Bases are the same, so I can add the exponents. Or if you didn't do that, 4 times e, that would give you this 10.873. So that's that problem. So maybe we're kind of working backwards here. Initial value problems, they're just generally when you're given a solution and you have to a solution to a differential equation and you need to solve for that constant or the plus c or the a in the differential equation. When you can solve for that by being given a point, that's an initial value problem. So these ones should be pretty straightforward then. You're going to anti-differentiate. You're going to plug in the point to solve for the constant that you didn't know, and go from there. So on this problem here on number 1, we separate the dy dx and then integrate both sides. So integral of dy is simply going to be y. Integral of cosine 2x dx is going to be 1/2 sine 2x plus c. I substitute in a 0 for x and a 1 for y. That gives us 1/2 sine of 0, so that's just 0 plus c equals 1. So c equals 1, and then I rewrite my equation replacing the c with a 1. Now on this next one, an arrow is fired straight up into the air with an initial velocity, and then we're given the acceleration equation. What that's telling us basically is I need to recognize that if I integrate acceleration, I get velocity, and then this v of 0 equals 155, that's an initial value. So I know that when velocity is 0, when time is 0, velocity is 155 feet per second. So I'll be able to use that to solve for c on part A. And then if the arrow is fired from an initial height of 5 feet, find the height as a function of time. That's giving me another initial value. So once I find my velocity equation, the height they're talking about is a position function, and so then I need to recognize that, so that I recognize I need to integrate the velocity function I came up with to get position. And initial again means time is 0 and height is 5. That's an initial value. And so when t equals 0, the position is 5 will help me solve for c on that one. Alright, so on this one, again, I'm going to integrate what I originally started with, which was dv dt is negative 32. And so that's the derivative of velocity or acceleration. So I integrate that, I get velocity equals negative 32t plus c. I knew from up here that when I plug a 0 in for velocity, I get 155. Now a lot of you would have just said, okay, the constant's going to be 155 because you recognize each term has a t in it, and the t is going to be 0, and that's all good. But technically, they like you to show the plus c and show how you solve for it, so that's what I did. And so I plugged the 155 in for the velocity. A 0 was plugged in for t and got me a c of 155, giving me velocity here. And then I took that velocity equation. I know if I integrate velocity, I get position, so I'm calling position s. That brings me down here. That's going to be equal to the integral of velocity. I integrate negative 32t. I'm going to have negative 32 times 1/2 t squared. Negative 32 times 1/2 is this negative 16. 155 becomes 155t, and I got the plus c. Then I was told the initial height is 5, so that tells me, maybe I should better change colors here. That tells me s of 0 equals 5, so I plugged in a 5 for position, plugged in zeros for t, got c equals 5, and my position equation then is what I have off to the side here. So those are nice problems where you need to apply an initial condition situation a couple of times. So I think that's really valuable to practice and make sure you understand. So ask questions if you don't get it. This one, I know people thought this was, and it was kind of hard to read here, but the velocity of the particle is negative 3 when t is 0. So v of 0 is -3 needed to be known on this one. So on this one again, we're given a of t, and so then we're looking for the velocity of the particle when we're looking for the velocity of the particle, or we're looking for what value of t will give us a velocity of 0. So I need to find the velocity equation and then set that equal to 0 and solve. And so I'm going to integrate and then set my velocity equal to 0 and solve. This would be a calculator active problem. Alright, so for number 3, I took that acceleration function, integrated it to get velocity, and I'm going to do the same thing for number 4. So number 4, I start with acceleration as cosine t, and so I'm going to integrate that to get velocity. I integrate that, and my velocity function is sine t plus c. I was told that v of 0 equals 0, so I set that up. V of 0 is going to be sine 0 plus c. Well, that means c is going to have to equal 0, so my velocity function actually is sine of t plus 0. And then I need to find my position function. I'm going to integrate velocity to get position. So I integrate velocity, integrate sine t dt, and I'm going to get x of t equals negative cosine t plus c. In this case, I was told x of 0 is 1 up here, and so then I plug in a 0 for t, and then I get set that equal to 1. I get c equals 2, and then my position equation is right there. For number 5, we're finding the antiderivative, or f is the antiderivative of g of x, given f of 1 equals 0. I'm looking for f of 5, and then you're given that hint to solve to find the function as the integral. Use the fundamental theorem of calculus. So that basically says we're going to let f of x equal the integral from 1 to x of t cubed over 1 plus t to the 5th dt. Then f of 5 is going to equal the integral from 1 to 5 of t cubed over 1 plus t to the 5th dt, and that's going to be about 0.6883. And so that's a nice way of knowing and being able to use your calculator to find an answer to such a problem with kind of limited information, or having a problem that you might not know how to anti-differentiate. That's a good type of problem to be able to know how to do, especially when a calculator is kind of going to be allowed on the test. Not saying I know that'll be on there, but that's a good one. So this last portion of this video will go over solutions to anti-differentiation by substitution. This is tricky. This is tricky for a lot of people, so I'll try to go fairly quickly, but also make sure I cover my thoughts on what I look for and what I recognize. I think what I might do is I might just use my solution set so it goes a little faster, and just talk through my solution set here. So here I've jumped to what my solution set is, and what I'll do is I'll zoom in on each problem and kind of talk through each one, but this will give you a chance to just check your answers first, and then we'll go from there. Alright, so I apologize. I know it's a little bit blurry here having such a big picture that I'm zooming in on, but so for this first problem, I'm basically looking at, for this question, you need to be able to see, or I probably should have used some parentheses here, that we're looking to integrate sine of x cubed, and that's times 3x squared. And so what I'm looking for is what I'm recognizing is I've got this 3x squared. Well, that has an x squared, and the derivative of what's on the inside of sine is actually 3x squared. It's perfect, but really all I needed was that x squared. The derivative of x cubed is 3x squared. So long as I had an x squared involved here, I was going to be set. So in this case, it works out perfectly, where if I use u equal to x cubed, then I differentiate u, I get du dx. I'm going to bring the dx over every time, over to this side. If I differentiate x cubed, I have a 3x squared. And so now, what I'm going to do is I'm just going to substitute in everything to get rid of the x's and replace them with u's. And so this, again, in this case, it works out perfectly where the x cubed, use a different, erase that here. The x cubed here is going to be replaced by a u, and so that goes right there. And then I have a 3x squared dx. Well, that is the du. Okay, so that 3x squared dx is the entire statement of du. So again, it works out perfectly. I'm just replacing that with a du. Now I can integrate sine u du, and I get negative cosine u plus c. I have to go back to my x variable, so I go back and I recognize u was x cubed, and so now I'm going to replace that u with the x cubed that it's equivalent to. If I go over to number 2 here, kind of similar. We've got in this one. Let me jump back. I'd like to be able to see this better, so I'm jumping back. So now we're looking over here on the right side. So on this one, what I'm recognizing is I have this 4x plus 3. Well, anytime I have a linear function in some spot, I can always replace that with a u, and its derivative is a constant. So I can always replace that if I want to simplify my integral. And so if I say u is going to equal 4x plus 3, then the derivative of u is going to be 4 dx. And so then when I go back to rewrite this, I'm integrating a 5 dx over a 4x plus 3. Well, 4x plus 3 is u. And so now the only thing I have left here is the dx to replace. Well, I don't have a 4 dx up here, so that tells me, well, I only have a dx to replace. Well, dx would be equivalent to du divided by 4. And so I'm going to write that in instead. So I'm going to replace the dx up here with a du over 4. And I'm going to do that by writing a du here and a 1/4 out front. And so I can simplify this even more if I bring the 5 out. So this would be the same as 5/4 times the integral of 1 over u du. And the integral of that would be 5/4 times, well, you have to recognize 1 over u is a natural log absolute value of u plus c. And then from there, I would just replace the u with what I started with. And that would be my answer. So again, some people would just do this one without a u sub because they can kind of look ahead and see, if it's a linear function where it would normally be a natural log that I get for a result, because it's a linear function that I'm dividing by, a constant divided by a linear function. You integrate that and you think natural log. If you recognize that since the x is being multiplied by 4, you're going to divide by 4 in integration, that's fine. You wouldn't need a u sub, but a u sub usually can save you some silly mistakes. Alright, a lot of times these ones with trig functions look pretty confusing, so again, I just kind of try to break it down and notice some things. So that 7, that's not anything I worry about. I just pull any constant out front, don't worry about it. And then I look at tangent. Well, tangent, that's the first trig function I see, so I'm looking at that, and that's raised to the 5th power. So sometimes it's easier to look at it as writing that this is tangent to the 5th. And then I start to think, okay, well, tangent to the 5th, the easiest thing is, well, if tangent could be the u, well then the derivative of tangent is secant squared. And lo and behold, secant squared is what's left. And so that's an easy u sub. So if I let u equal tangent, and then du is going to equal secant squared x dx, I've got everything that can be replaced. The tangent x is going to be u secant squared x dx, is going to be the du. I don't have too much left to do. So I've got 7 times the integral of now u to the 5th, because tangent's being replaced with the u. And then the secant squared x dx, well, that's du. And so that's a pretty easy integral to solve then. Now I have 7 times 1/6 u to the 6th plus c, and so then I'll have 7/6 u is tangent, so 7/6 tangent to the 6th x plus c. So that's kind of a nice one. Over here I'm noticing on number 4 we've got a x squared minus 4, so that's a second degree polynomial, and it's being multiplied by a 4x dx. That's a first degree. So anytime I've got a second degree polynomial inside of a function and that's being multiplied by a first degree, well, they're a derivative difference from each other. And so I would look at this as that x squared minus 4, well, that can be my u, and then du is going to be 2x dx. And so then if I go back and look at this first integral, that's going to be the same as integrating 4 times, I guess I would say. I'd look at that as 4 times the integral of x dx over x squared minus 4 to the 1/2. And so then when I look at it that way, I don't have a 2x dx, I just have an x dx. I could pull a 2 in from here, I could bring one over, but generally students don't want to do that, so I'll just instead divide by 2 on both sides, so I'd have a 1/2 du equals x dx, and now I can substitute in fairly easily. I'd have 4 times the integral. The x dx is going to be a 1/2, so I'm going to put that 1/2 out front, and my x dx will then be a du, dividing by x squared minus 4 to the 1/2, so that's just going to be a u to the 1/2. And this should be pretty easy to integrate then. What's on the outside is going to be a 2 times the integral. If you want, you could write it as a negative 1/2 du. So that's going to turn into 2 times, okay, u, if I raise u to the negative 1/2 by 1, I get u to the 1/2, so that's going to be times 2 u to the 1/2 plus c, so I would have 4, and then u is x squared minus 4, that's raised to the 1/2 plus c. Now on this one, what I recognize is I have a cosecant something times cotangent of the same thing, and in my mind right away I think, well, cosecant cotangent, that's the derivative of something, and I'm integrating. And so in this case, it's this x squared. It's this x squared in here that I notice, and then we're multiplying by an 8x. So again, second degree polynomial on the inside of a function times a first degree polynomial dx, though they are a derivative apart. And so my mind is thinking, well, I'm probably going to want u to equal x squared, then du is going to equal 2x dx. And I've already got an 8x dx out here. I'll just show you that other way of thinking. If I pull a 4 out, this integral shown is going to be the same as 4 times the integral cosecant x squared cotangent. Oh, looks like I'm getting too long into the video here. Cosecant x squared cotangent x squared times 2 dx. And so then that's going to allow us to substitute in nicely. So I didn't realize the video would end, or I'd have a time limit. So if I substitute those in, here's that cosecant cotangent with u substituted in. Look that over. On this one here, we've got integral of 3 to the natural log of x over x. I see natural log of x, I see 1 over x dx, that's a derivative, so there's my u sub there. And kind of go from there. Maybe I'll leave you at this, show you the other solution again. So here is the rest of the solutions to that assignment. So you can take a look and let me know what else you need help solving.